Well, let's see what we can do. How big is the universe is a very old question. And the answer depends on whom you ask and when. And it's a difficult question to answer for the same reason the best oceanographers are not fish. We live inside our solar system, inside our galaxy, inside our universe. And it's just not the best, that'll probably work. That's not the best possible vantage point. And there is my name in customary blue and my name in Egyptian hieroglyphs. I started life wanting to be an archaeologist, and I never quite got over it. And funding from the Internal Revenue Service. And there is a hopeful scientist, female based on the clothing, not on the anatomy, and trying hard to decide what size he, she, or it is. Notice that's a logarithmic scale and not doing a very good job. So I want to start with what our ancestors thought for as far back as we can find records of what our ancestors thought, and move forward fairly quickly through human history. And that will involve taking us to larger and larger distances, and therefore looking further and further back in time. Telescopes are time machines. The light travels at the speed of light. Isn't that amazing? Gravity, as it happens, also travels at the speed of light. We've known that for 100 years, because when you calculate things in general relativity, you use a little symbol c that actually means the speed of gravity in the equations. But when you put in the speed of light as the right number, you get the right answer. People have done more precise measurements of that more recently, but we've known for a long time that gravity travels at the speed of light. So telescopes are time machines. And so there we are, University of Manitoba, Winnipeg, Canada, North America, Earth, Solar System, Orion R, Milky Way, Local Group, Virgo, Laniakea, Universe, and a habitable multiverse. We'll come to that at the end. Past bets. Every time in the past history of science, when there's a group that says there's only one of those, and somebody says, they're common, the common have been right. Anytime anybody said, that's small or young, and some other group has said, well, that's big and old, the big and old people have been right. And so I'm betting that will continue to be true. And we will discover that our universe is not unique. Many, one, monotonic, yes. There have been some steps backwards. Big one, monotonic one. Let us start with our ancestors. The ancients, the Greeks or the Egyptians, I'll show you a picture in a minute, were pretty sure that the Earth was the universe. A human being could get around it in a lifetime, and a god could get around it in a day, like Helios in his chariot going around the Earth, or in the Egyptian case, that's Panku. Panku separated the sky from the Earth by growing 18 miles a day for some long period of time. This is the Egyptian version. There is Ra in his sunboat riding up in the morning and down in the afternoon. There is the sky goddess Nut, held up by the air goddess Shu, who stands on the earth god Geb. And their names are there in hieroglyphs. I have another favorite version of this picture. That's the one you're not allowed to show in polite company, owing to the way he's supporting the goddess. So for the ancients, the Earth was the universe. It wasn't very big. The best Greek numbers, these are the Greeks that are contemporary with people like Plato, thought that the moon was about 270,000 miles away, very close to our modern value, and they measured it, an honest-to-God measurement, by looking at the shadow of the Earth as it goes across the moon during an eclipse of the moon. And the different curvatures of the limb of the moon and the shadow give you the relative sizes. And they measured the size of the Earth, and therefore they knew the size of the moon and its distance. The medieval period, there was a certain amount of retrogression. That's a shrunken universe from the 6th century. You wouldn't want to live there. However, I'm told Manitoba has only one hill and it's made of garbage. This Earth had only one hill. It probably also was made of garbage. There's the universe of Hildegard of Bingen. She also wrote music, and she had migraine headaches that produced some very interesting artwork. She wrote very early polyphony. And notice her universe didn't have to be spherical or circular, sort of pineapple shaped, and some of the things are in the wrong place, but it's an interesting universe. That's not really an ancient universe, but it's an idea. There you live on the surface of the Earth, the moon and the sun going around the Earth, yeah, right? And you look outside by sticking your head through the sky, And there you find the prime mover taking the sky around you. Nobody ever really believed it was quite like that, but it makes a nice picture. So the ancients, the Greeks, and we now invent a new unit to measure distances. We're going to call it the astronomical unit, because it's used in astronomy. Isn't that amazing? But the point is, it's the average distance of the Earth from the sun, and we'll use that to measure distances within our own solar system. Please do not put the podium on the floor. Someone can trip on it. There is the universe as envisioned by Martin Luther. I read the Augsburg Confession quite recently. It's a very interesting document. If you happen to have even very basic German, it's worth reading in German. If you don't, there are translations to be had. But it's what he thought people should feel and do and think about the world around them and God and so forth. And God's pretty big in that picture, you will notice. That is another one of the Earth-centered universes. That one doesn't just have God, that has 7 orders of angels outside where the stars are. That dates from 1493. That's a famous year, right? In 1493, Columbus sailed the deep blue sea. That's what I learned in childhood. He crossed the Atlantic 4 times. So there we have the ancients. Oh, we're going to recapitulate each time, but I'll make the recapitulations really quick. So the ancients, the best Greeks, our estimates of the distance from the Earth to the sun get better and better, from Hipparchus to Copernicus to Tycho to Kepler to Herschel to Huygens, who has essentially the modern value. And if you are a native speaker of Dutch, you can say his name much better than I can. But he's been dead for many centuries, so he won't come anyway. There is a curious version of trying to please everybody. The Earth is at the center. The sun is going around it. That's the one with the hair. And the sun carries Mercury and Venus with it. And then Mars, Jupiter, and Saturn go around the Earth, and the stars are all out there. But notice the stars are in just a thin shell all the same distance from us. But progress is made quite quickly beyond that. The ancients, the astronomical unit. Meanwhile, the Earth-centered or Ptolemaic system was being replaced by the sun-centered solar system. And Saturn was out there at about 10 times the distance to the Earth from the sun. And were the stars all just in a thin shell? No, maybe not. Diggs has an infinite universe already. But the real question at that stage was, how far is it to the stars? How big is the universe? Here's our little solar system, 10 AU across. The stars have to be much further away, but how far? How big is their universe? So there's Copernicus. Copernicus didn't do all the things he's blamed for. So Yogi Berra said, I didn't say all the things I said. Famous sayings that aren't true. But Copernicus started with circles and he made it better. Copernicus needed just as many epicycles as Ptolemy, but putting the sun at the center made everything look much simpler. And there on the right is Diggs, a little before 1600, sun at the center, the Earth going around it, and all the other planets. And notice that he has stars all over the place, but he runs out of paper. His text says the universe is infinite, but paper was really expensive in those days, so he couldn't draw an infinite universe. And that's been a problem ever since, how to draw an infinite universe, seriously. Yes, now we're going to go forward by trying to figure out how far away the stars are. That's a distant star on the right. On the left is the sun at the center, the Earth going around it. Distance from the sun to the star is called d. You measure that little angle, and because you know the distance from the Earth to the sun, you can then do a tiny bit of geometry and learn the distance to the star. The catch is, for a very long time, nobody could measure that little angle, which meant that the stars had to be really far apart. And that worried some people. Why would God have wasted all that space? Why is there so much almost empty space? It isn't really empty, it's full of hydrogen and dark matter. But people worried about the space being wasted, and so they weren't quite sure they liked that picture. However, the telescope came along. On the left is Galileo's drawing of the Pleiades. On the right is a photograph of the Pleiades, turned 90 degrees, of course. But with that, you could see not only many, many, many more stars, but there was stuff between them. The space wasn't all empty. It wasn't all wasted. This is Descartes, famous for Cartesian coordinates, a philosophy, and for a picture of the universe. The center there is our own solar system, but there, C and L and O and K, those are other stars with their solar systems. And he's only put ours at the center because he didn't have very much paper. It doesn't mean that ours is more important. He recognized that there were other systems of stars with their planets, not different from ours, or not very different. And the minute you say that the stars are suns, or that the sun is a star, you can begin to estimate how far away they are. How big is the universe? It gets bigger. Yes, ancients, the Greeks, stars are suns. And many people said that. The one you're supposed to have heard of is Isaac Newton. And he put Sirius at 1 million astronomical units. There was James Gregory and John Mitchell. John Mitchell was a fascinating guy. He did many, many things. He had a theory of black holes long before general relativity and Einstein. But there are no pictures of him. He was a clergyman. Apparently, he just wasn't very good looking. He didn't want any portraits. There are an infinite number of portraits of Newton. There are none of Mitchell. It's very curious. But starting in 1835, I remember it well, right? People started being able to measure that tiny little angle and had to invent a new unit. They called it parallax, and the unit was the parsec, for parallax second. It's a second of arc, not a second of time. A second of arc is the size of a dime a mile away, or if you have some Russian coins in your pocket, it's the size of a kopeck, additions of a kilometer. Anybody got any Russian coins with them? I don't think you're allowed to bring them through customs here, actually. I never know what I'm allowed to do in different countries. I'm terrified, absolutely, of the Internal Revenue Service. The second thing I'm terrified of is the Department of Motor Vehicles. They can take your driver's license. And the third thing I'm scared of is the Transportation Safety Agency. The police are a very distant fourth on this list of terrors. They also can take away your life. Anyway, the parallax second gives us a new unit for distances of stars. And the very nearest stars are already more than 1 parsec away. In other words, you have to measure these angles that are less than a second of arc. And Thomas Wright, having done some of this, thinks the universe looks like that. It's a slab. The sun is kind of near the center. But that's the nicest version of his drawing. Herschel and Kapteyn say that there is a system of stars called the Milky Way, galactose, the Greek word for milk. Galactose is milk sugar. Some people are allergic to it or can't process it or something. In any case, that is the Milky Way, and the solar system they thought was near the center. It was about 10,000 parsecs across and 2,000 parsecs thick. The stars are suns. You count them to see how many there are in different directions. It defines the galaxy, with the solar system fairly near the center. Ah, yes, there is William Herschel's galaxy. Again, a thin slab with a circle around it, and the solar system fairly near the center, not exactly at. And this is Herschel again, putting the galaxy as a sort of disk-like thing with frilly edges, and the solar system, which is the circle with the dot in it, near but not exactly at the center. This is Sir Arthur Eddington. You're not expected to have heard of Eddington, unless you are interested in history of science and stuff. You probably are expected. Where is my little cluster of biologists? You were together at lunch. Are you together here? Okay. Have you heard of Alfred Russel Wallace? Ooh, they've been neglected. He's the guy who forced Darwin to publish by having the same ideas a little earlier. And they leaked back to England. He was in New Guinea or someplace like that. They leaked back to England, and that persuaded Darwin to publish. But Darwin is famous and Alfred Russel Wallace is not. But there's a picture of the Milky Way that is very strange. It's a central cluster and blobs on either side. But again, the solar system is near but not exactly at the center. And this is Kapteyn's universe. Again, the solar system near but not at. And at this stage, between, say, 1900 and 1920, there were two competing theories of what the universe is and how big it is. There were people who thought that the Milky Way was the entire universe. It was pretty big. There were other people who thought the Milky Way is just one of many galaxies. Now, what did we say when there's a one and a many competing? Who's going to win, the one or the many? Holler. Amen. That's right. There are many galaxies. And the Milky Way is a pretty average one. And getting that sorted out required two things. Well, it required three things. It required work of Henrietta Swan Leavitt, who doesn't get much credit because she was the wrong gender and the wrong age and all that. She was paid 50 cents an hour when men were paid $1 an hour. Or maybe it was 50 cents a day, but they got half the salaries that men do. There's still some of that around, at least in the US. I don't know if it's true in Canada or not, but for the same job, women are typically paid a little less. It was a lot less in those days. So there is Henrietta Swan Leavitt figuring out that the brightness of stars of a certain kind that pulse in and out is proportional to the period with which they pulse, from 1 to 10 to 100 days, and luminosities from 100 to 1,000 to 10,000 times that of the sun. Plotting things on a log-log plot is an excellent strategy when you don't understand a phenomenon. I had a colleague in Cambridge who said he proposed to plot me on log-log paper. He's dead. And with this way of measuring distances, here's a guy fighting with his conscience and losing. That S is where he's put the solar system at the center of the picture, but the spiral arms of the galaxy are centered somewhere off to the side. He's right in some senses. That's another version. 1909, there's a central cluster of stars, there's an outer ring, and that B is a location of our own solar system. And here is Henrietta Swan Leavitt, who understood the period luminosity relation for Cepheid variables. Somebody nominated her actually for a Nobel Prize, but it was after she was already dead. And Nobel Prizes go to only living people. They also go to only 3. How many of you have heard of LIGO, the laser interferometric? Okay, I've written a LIGO fight song. I'll sing it with you afterwards. The LIGO team's a mighty core, 1,000 strong or even more, but prizes go to only 3. Ray Weiss, Kip Thorne, and Ronald D. And so forth. Okay, she developed the tools that enabled people to measure distances and get us out of the center of the Milky Way, and then to recognize that there were other galaxies. There's somebody, again, trying to fight with his conscience, putting the center of the distribution of clusters of stars off to the right, and our little tiny bit, that little sliver living where the crosshairs cross. Oh, the circles at the bottom are 2 small galaxies that orbit ours. They're called the Magellanic Clouds. They're only visible from the southern hemisphere. And therefore, Magellan was the first person to see them. How many think that Magellan was the first person to see the sky from the southern hemisphere? Okay. Strangely, there had been many people living in South America and Australia and Africa. This is another version. Shapley got us out of the center of the Milky Way by locating star clusters using these Cepheid variables. And here is Oort trying to have everybody get a prize. There's the Kapteyn version, and there's Shapley. And there is Oort trying again to give everybody a prize. Oh, can you see? Yeah, you can see the bottom line of that. If you know what country Oort must have come from, holler it. No, holler. Louder. Yes, that's the line at the bottom is Dutch, but because it starts out Dr. Oort's diagram, it doesn't. You have to go one more word to realize it's in Dutch. Yes, Oort was from Netherlands. And here's Plaskett. This is 1939, which is essentially the modern picture of the Milky Way. A disk of stars, the solar system, notice, is off to the side now. And then there was a war, which I do not quite remember. I was born in 1943, so I don't quite remember. But there are people still alive who fought in that war. Not very many, but some. They're dying off now very rapidly. Some quaint statistic in the US, like there are 200 World War II veterans who die every day or so. We're losing that piece. If you have an old relative, collect their stories before they're gone. Someday you're going to be the last person who remembers something. But there we are now with a universe that's at least 100,000 parsecs across. It's growing like mad. And here we have a modern view of the galaxy. The Gaius satellite, it also slices bread if you need that done. And it measures a whole bunch of things about the Milky Way out to considerable distances. So we had the Greeks The astronomical unit, the heliocentric universe, stars are suns, parallaxes, Cepheid variables. And at this point, we meet Edwin Powell Hubble, who finds Cepheids in M31, the Andromeda Nebula, and therefore shows that Andromeda is a separate galaxy. It's not part of our Milky Way. He does that in 1923, 24, 25. Other galaxies exist, and they have distances that are at least millions of parsecs, compared to thousands for our own Milky Way. What were these people thinking of when they named their children? Here's Heber Doust Curtis. I had to phone his last student to find out how the middle name was pronounced. He said, they're wrong with Soust. So here's Heber Doust Curtis, who had no use for Einstein. And there was Vesto Melvin Slipher, who started measuring velocities of galaxies. What were these people thinking of? I'm named for my mother because in those days, women were unconscious when they gave birth. And they picked, I was supposed to be a boy named William Starling. And so when I turned out to be a girl, my father said, name her Virginia, which was my mother. So for years, we had Big Virginia and Little Virginia. Yeah, right. It's a beastly thing to do to a kid, actually. And not very nice for the mother, actually. It's to be known as Big Virginia. Members of our family have fought the Battle of the Bulge for centuries. And here is Heber Doust Curtis discovering star explosions in other galaxies, and thereby recognizing that these are other galaxies. And there is Edwin Powell Hubble looking at Andromeda on the left and recognizing a particular star as a Cepheid variable. The photograph on the right is a little bit hokey, but he really did always wear a suit and tie, even when he was observing at the telescope. So now we have, from the ancients to the Greeks, the solar system, stars are suns, there are lots of them, other galaxies exist, and again, Hubble showing that the galaxies are moving away from each other. It's not that they're fleeing away from us, though you might think they would want to, but all galaxies are moving away from each other. This gives us another new unit called redshift, which is the change in the wavelength of light that we see divided by the wavelength in the laboratory. And a distance that is that redshift times the speed of light is equal to some constant times the distance. And the distances when Hubble first started were just a few million parsecs. But our ability to measure distant things far away and make the universe clearly larger and larger has continued from that day to this. Those are data before Hubble. You could actually have discovered Hubble's law a few years earlier. And there's Hubble's version. The scale is wrong because he's using the numbers that came from Shapley, which were wrong for complex reasons I won't try to explain. But his distances are too small by about a factor of 10. And that's going to take a fair amount of sorting out. And we express what needs to be sorted out as a numerical value of the Hubble constant, which Hubble said was 530. Funny units. Kilometers per second per megaparsec. That is no way an SI unit. Is there anybody here in the room? No, there's nobody here as old as I am, but there may be a few of you who agree that the universe was created in CGS and all their units are man-made. SI. Psh. Now, we're at the stage where there are many galaxies, and people start arguing about the actual scale of the distances from the galaxies, which in turn tells you the age of the universe. Telescopes are time machines. The further things away are, the longer it takes the light to get here, the older the universe has to be. And so the universe, as we see it, is going to be getting bigger and bigger, not because it's expanding, but because our measurements are changing. And at the same time, it gets older and older. This is what happened after Hubble. He's in the upper left-hand corner there. And the dotted pink line, I apologize to those of you who are pink-yellow colorblind or black-blue colorblind. When I was a graduate student, we plotted this kind of thing, and it looked as if the numbers were going to go through zero pretty soon, and the universe might start contracting. That didn't happen. Most things, if you have some kind of thing you can measure over time. For instance, the winning speeds in I don't know, the winning speeds in marathons, that's a good one. The first few marathons, it took a long, long time, and then the times dropped really, really fast. And now they've leveled out again. The winning times in marathons have changed only a few minutes over the past decade. Horse races, it's even less than that. It says we're breeding horses more efficiently than we're breeding marathon runners. But in any case, the same thing I think was true for our understanding of the size of the universe, that it was steady at large Hubble constant, small universe, and then things change rapidly. He's making a strange noise besides me. Okay, yes, that one. It's a necklace banging against the microphone. That is very clever of you. We can cure that. Yeah, okay. And then it levels off with the kind of value you get from the Hubble Space Telescope that goes with the universe being 12 or 13 billion years old. So the universe has gotten bigger and bigger. Oh, this is just for fun. People were trying really hard to measure the Hubble constant. This is the values measured versus the poster number at a conference a few years ago. Okay. But you know, it looks like a pretty good correlation, doesn't it? That was about the time people stopped asking me to give concluding remarks at conferences, I think. But here we now have, we've started with the ancients, we've worked up to Hubble's law and redshift as a unit. And now as we have bigger and bigger telescopes and more sensitive detectors, going from photographic emulsions to electronic detectors has made an enormous difference. We've been able to measure larger and larger redshifts. The largest one that Slipher measured was 0.003. There was Humison and Minkowski and Martin Schmidt, that was the quasar. And the Sloan Digital Sky Survey, down to about 20 years ago. And it happens in jagged steps with new telescopes, new spectrographs, new detectors. And redshift bigger than 1 doesn't violate anything. You've undoubtedly been told in early childhood that nothing is allowed to travel faster than the speed of light. That's perfectly true. But the formula for the Doppler effect that appears in elementary textbooks is wrong for all models of the universe. That just isn't how general relativity works. GR is, in some sense, conceptually very simple. The distribution of mass energy in the universe determines the geometry. Now do the arithmetic. Anybody who's ever taken, how many of you have taken or taught GR at some point? A few. And you also cluster like the biologists. That's very interesting. But the arithmetic is remarkably difficult. Einstein himself knew this. When he first was sent by Karl Schwarzschild the solution for what we now call a Schwarzschild black hole, he writes back and he says he's astounded at how simple the solution is. That was the only simple solution. And anything else is now computer simulations, numerical calculations, ... computer algebra. But the relationship between redshift and distance is a complicated one, but it's not so very different from linear, and it does not involve any speeds faster than the speed of light. We see an awful lot of galaxies. Everything in that picture, literally, is a galaxy, and the ones that are circled belong to certain clusters. The universe is getting bigger. The ones with the boxes around them are really very, very different. One of them has a redshift of almost 10. The most distant object seen, the most distant individual object seen, we see radiation even more distant than that. But small galaxies were assembling when the universe was less than 1 billion years old and had another 12 billion to chug along. So the universe is getting bigger and older. Now, we start with the ancients. The maximum redshifts we see for galaxies and quasars and gamma ray bursters is 6 to 10. It continues to grow, gory, yeah, right? I'm a moderately good typist, I'm a lousy keyboarder. They're different skills. It's like piano and organ. Anybody here play both piano and organ well? Anybody play one or the other decently? Have you tried the other? Oh, try the other. I don't care which one you play, try the other. They're very different fields. And the keyboard of an old-fashioned typewriter is very different from the keyboard of a computer. And I'm a better typist than I am a keyboarder. Okay. But the measured values that we can find as our telescopes get bigger and our detectors get more sensitive, those redshifts keep getting larger and larger until we find, we're looking back before many galaxies had formed, so we don't find any more because they didn't exist. But at a redshift of about 1,000, we encounter radiation left over from the early hot, dense universe. It's called the cosmic microwave background, CMB, thermal isotropic relic of a hot, dense universe. Another misspelling, sorry about that. The concept of the Big Bang has caused a good deal of fuss and bother. The thing that we have evidence for is that 12 or 13 billion years ago, all the matter that we can now observe was hot and dense. It doesn't mean it was a single point. It doesn't even mean it was a finite volume. Just everything we can now observe went through a phase of being very hot and very dense. That is the hot Big Bang for which we have evidence. If you want to say that there was a time equals 0, and that was the Big Bang, you may say so, but not to me. Because if you say it that way, then you've got to do a bunch of very fast song and dancing to let the universe expand, which makes it cool, and you've got to reheat it. Because the evidence we have is for this hot, dense stage that made about a quarter of the ordinary stuff be helium when it started out as hydrogen, made nuclear reactions, and it left the radiation, which we now see as the cosmic microwave, and I may even have a picture of it. Transformed, of course, to visible light. There's an excellent reason that we don't have creatures who are microwave sensitive. You need an eye that's about this big, and all the animals with microwave eyes, their heads fell over and they died. More galaxies. Yes, that's the standard picture of the microwave background. It's simply a plot of the hot and cool regions. And the difference between hot and cool is incredibly small. The original discovery, Penzias and Wilson, and many other people claimed it afterwards, of course, like the number of people who claim to have invented the automobile or whatever, or the refrigerator. Actually, the refrigerator was invented by a Russian named Westinghousky. That's what they told Nixon when he visited. The discovery of the microwave background was credited to Penzias and Wilson, 1965. And as far as they could see, the temperature was the same over the entire sky, to about 10%. We now know that it's actually the same over the entire sky to a part in 10,000 or better. And it's these very tiny variations that represent lumps in the distribution of matter that are going to grow into the galaxies we now see. So this is a picture of the infancy of the universe. It's after the hot Big Bang. The gas at this stage is cool, and it's even cooler now. It's down to 3 Kelvin. It was 1,000 Kelvin when this picture was not taken, but when the radiation in this picture left the gas, its temperature was a few thousand Kelvin. So, the observable universe, light has traveled almost 14 billion years, and the universe has continued to expand since then. So the sources of that radiation are now 46 billion light years away from us. And the structure now is complex filaments, voids, galaxies, and clusters. Yes, those are observations. Every dot in that is a galaxy. And that's a better one. Every dot is a galaxy. The redder ones are older. The bluish-green ones are younger. A complex structure, a hierarchical structure of filaments, surfaces, voids, galaxies. And the people who do the calculations say you start with the fluctuations that you see in the microwave background and let gravity work. And eventually you end up with the kind of structure that we actually now see in our distribution of galaxies into the void. And the empty spaces in between are interesting as well. So we have an observable universe that is 13 or 14 billion years old. The real universe size is much larger than the observable size. We see no edge effects. It's like looking down a highway and you do not see any end to that highway. It doesn't mean it doesn't have one. It just means that the highway is big compared to the part you can survey. And that is true of the universe. It may be infinite. The age is finite, but that's okay. It's been allowed to expand as it wants, as it were, in accordance with general relativity, with these difficult, tiresome calculations. Is this the only universe? Not necessarily. There is a later stage where you've grown to have clusters of galaxies and filaments between them. And we then ask, can there be other space-times? The part we see is small compared to the total, which could be infinite. There could be many other non-communicating other space-times with different physical laws, forces, and particles. But they almost certainly have 3 spatial dimensions and 1 time dimension. There are different ways of thinking about this, but if there's more than 1 time dimension, there's no causality because there's always more than one way of getting from an event to another event. And in some cases, this will cause that. In some cases, that will cause this. So a universe that has more than 1 time dimension will not have processes that go monotonically from simple to complex. You would have politicians evolving into slime moles instead of the other way around. Yes, evolution is what turns slime molds into politicians. And in the absence of a single time dimension, you cannot define that as a single process. The issue of spatial dimensions is more difficult. Anybody remember reading Flatland when you were in high school? Yeah. The problem with a two-dimensional space, you can do it a different way. You can have the three houses and the gas pipes and the electricity and the water, and you need to bring all three services to all three houses without the things crossing, and you can't do it. It just isn't possible. You can't have complex structures in two dimensions. If you go to 4 dimensions, you don't have stable orbits. If you have 1 over r squared gravity, you get stable orbits in 3 dimensions. If you have 4 dimensions, there's no simple form of gravity that will give you stable orbits. So you cannot have things that stay at roughly the same temperature for long enough for life to evolve. So we suspect that other universes will have also 3 space dimensions and 1 time dimension. There's some wonderful science fiction built around this kind of stuff. There's some stories by John Wyndham that I absolutely love that take seriously a man named Hugh Everett, who decided that any time a quantum process occurred, an atom decayed or something, the universe split and both things happened. In that universe, that atom decayed. In that universe, the atom did not decay. And in this universe, Schrödinger's cat is alive. In that universe, Schrödinger's cat is dead. In that universe, Schrödinger keeps dogs. So, not just one Earth, many planets, thousands known now, of course. Not just one sun, thousands of stars. Not just one galaxy, but billions of galaxies. And every time we look at, we see further, and things take longer. And the trend of this is very much in the direction, I think, of there being other universes with other physics. Oh, yeah. Spectacular, isn't it, son? In fact, astronomers say there may be billions more little white dots beyond the border of this cartoon. The same problem of the finite piece of paper. And this is a chap trying to describe a multiverse. He says, in some universes he's rich, he's a movie star, he's king, he's also poor, homeless. Lots of him are dead. And in some universes, Rowan Hooper. And it is not quite true that this is not a testable hypothesis. That may sound convoluted, but it's the right way to say it. His science has often made progress by having an idea and showing it was wrong, and having another idea and not being able to show that that's wrong. Other galaxies exist, what have you. But my favorite picture for a multiverse is not Ryan Hooper. I don't know whether he's good looking or not. Notice he has his back to the camera the whole time. My favorite view of a multiverse is much more like Hugh Everett's, where each time something happens, branches spread out so that that's what a multiverse looks like. And I think that's a pretty picture. And you have one or more hot, dense phases in the past, and other universes spread out around each other. And I still think that's the best bet, that many stars, many planets, many galaxies, many clusters, probably many universes as well. And I think I was supposed to stop at 4:15. I believe it's now 4:15, so I'll stop and invite questions, comments, or rude remarks. Would our chair like to take over, or has our chair departed? Oh, yeah, act like a chair. No, act like a chairperson.
Questions,
Comments, rude remarks.
Start with rude remarks. Please, does no one have a question?
I have a question.
Okay, go for it.
Do you think an event in this universe might affect the events in other universes, or they're totally unrelated?
If I knew that for sure, I could probably make money from it. There have been suggestions of universes colliding one way or another. The brain theories are like that, where they do that and they heat each other and go back again. And people have thought a couple of times that they saw sort of smashed places as a signal in the microwave background that would be another universe colliding with ours. I think the evidence for that has largely gone away. That doesn't mean it isn't possible. So the answer to your question is maybe, which I realize isn't very helpful. But at any given stage, you have a lot of questions which the answer is maybe. Was there a single last common ancestor before the very simplest protozoan that we've ever met? Maybe, and many other things. So I don't know, but it's certainly possible. Yeah.
Do you think other universes could be related to this concept we call heaven?
You call it what you like. Okay. It's been suggested, of course, that ghosts have slipped from a nearby universe, or the day that your spouse doesn't act like your spouse, it's actually your spouse from the adjacent universe visiting. Okay. I'm third-generation atheist, so I'm the wrong person to ask that question of. I can't say the answer is no. I can only say that for me, the question is meaningless, because my universe doesn't have a heaven.
Okay. More questions? Yeah.
How far back can we look in the universe and say that gravity had an effect on things? Like, did gravity come to be at some point, or has it always been in existence?
Yes to both of those. Okay. The things we do know are, if you go back to a fairly high temperature, electromagnetism and the weak interaction were the same. And they split, I don't know, billions of degrees. You go back further, electromagnetism, weak interaction, and the stronger nuclear force were the same. Gravity doesn't join up with the others, and we can't make it do so, because gravity is not a quantum theory, GR is not a quantum theory, and can't be made into one. So as far back, or as high a temperature as we can look, we can't tell what gravity was like, because you can't bring it together with the others. Certainly at the time of the microwave background breaking loose, you know gravity was working, because you see this structure of high and low densities, so you know gravity was working then. But how much further back, I don't know, because we don't know the right theory of gravity. I mean, Einstein himself said, though he, not for the right reason, he said that his GR had replaced Newtonian gravity, and he expected that there would later be another better theory. I don't think he would have wanted it to be a quantum theory. Einstein was not fond of quantum mechanics, but he expected there would someday be a better theory, at which point maybe that question could be answered.
Yeah. Question over there? Yeah.
Maybe I understand that my understanding of this is very limited. But
Mine too, carry on.
I find it hard to understand the concept of gravity moving, as you said, like light is moving. Can you elucidate that?
Well, okay. Electromagnetic radiation, otherwise known as light, has a particle equivalent, otherwise known as photons. And they travel at a definite speed, carrying information from one place to another. Now, in the context of gravity, also something happens. That information has to propagate outward at some speed. And there was a time when people actually doubted that that propagation carried energy, but that was settled in the 1950s by many people. But the process that carries that energy outward, you can call it gravitational waves, gravitational radiation, you can call it gravitons. Feynman always said gravitons. But the information about a change in the distribution of mass energy has to travel at some speed. And the observations tell us that that speed is very close to the speed of light, if not exactly identical. It gives you a limit on the mass of the graviton, if you want to do it that way. 10 to the minus 63 grams.
Here's a question here.
Mm-hmm. So as telescopes are getting bigger and more powerful, we're able to look further and further back into time. Mm-hmm. Is there a theoretical limit to the Hubble constant that we can go right back to 13.8 billion years, or is there a limit that?
The limit doesn't come from the Hubble constant. The limit comes from the fact that at a redshift of 1,000, the universe is opaque. Light just scatters. It doesn't propagate. That's a universe at an age of about 100,000 years. Whereas interesting nuclear processes happen in the first few minutes. That Steve Weinberg's book, The First 3 Minutes, deals with that nuclear era.
Why is it opaque?
Because the gas is ionized. Electrons love to scatter light. Dust also loves to scatter light, but the early universe doesn't have dust because it has no heavy elements. But free electrons love to scatter light, Thomson scattering, all that stuff. So you go back to when the matter was ionized, and you can't look through it with photons. You can look through it with neutrinos if you can figure out how to do it. You can look through it with gravitational radiation if you can figure out how to do it. But photons you cannot look because the universe is opaque.
So right now we can see down to 13.4?
Well, yeah, fair enough. Fair enough. Well, no, I think you're confusing thousands with millions. But the microwave background that comes to us from a redshift of 1,000 roughly is a universe that was 100,000 years old out of 10.
By any current techniques, you see.
Well, we see that microwave background, and we see it as it comes from the way the universe was at an age of about 100,000 years. And you use radio and microwave telescopes for that, not visible ones. But again, the universe at that stage is opaque to radio waves as well, and gamma rays, and any kind of electromagnetic radiation you happen to be fond of. I like infrared myself.
Can we see the first generation of stars?
Yes, but the first generation of stars is what makes that universe be transparent again. It's called reionization. We see stars that are almost first generation that have actually survived. They're signified by having almost no heavy elements. The sun, solar system, about 2% heavy elements, mostly CNO. But we see stars whose component of heavy elements is smaller by a factor of 100,000. They're almost, but not quite, the very, very first generation.
There's a question way back up there, I think there was. Yeah, go ahead.
Yeah, so this question's more of a question on the history of science. One thing that's always really fascinated me is it seems like in the middle 1900s there was a boom in theoretical advancements in biology, in astronomy. Mm-hmm. Was that a random effect? Was there something happening with kind of the intellectual production in terms of
No, it was certainly not random. It was not random at all. And you can say it different ways, but what basically drove it was World War II and the immediately subsequent Cold War that put money into better technology and into educating people. If you have 10 scientists, you won't have 10 times as many ideas as you have for one, but you're going to have many more. And if you build a much better telescope, you're going to see not just more things, but different things. If you build a microscope, you build a scanning, STM, build a scanning a scanning tunneling microscope, you're going to see stuff that you didn't see with your light microscope. And what put money into technology and money into educating people in the sciences was World War II and the immediately following. You're all too young to remember, but right after Sputnik launched, the US suddenly had a lot of money to educate physicists. I benefited from that. I mean, my graduate school was largely paid for by that kind of money, fellowships. So it was not random. And the fact that many fields jumped at the same time was not a coincidence. There are people who have said that, every advance has come from warfare. I don't think that's true either, but a lot of them have. Yeah?
Way back there, yeah.
No, and then her next. Well, okay.
The lady way back there.
Yeah. You got to be louder.
What are your views on black holes and time-space singularity?
I got the black holes. What's the other one?
Time-space singularity?
Time, space, singularity.
Oh, okay. You're never going to see one, so it doesn't matter. The idea of things sufficiently compact that the escape speed is larger than the speed of light comes out of Newtonian physics. I mentioned John Mitchell for just a second. He did it, also one of the French guys at the same time, late 1700s. And as it happens, the basic Newtonian calculation gives you the right answer, R equals 2gm over c squared. Compact things, light will not get out, and that's a black hole. Is there a singularity at the center? I don't know, I've never been there. And people who do the calculations find that the stronger the gravitational field, the closer you get to a really, really compact distribution of matter, the harder it is to do the calculation. Do world lines end there? If basic GR is right, yes, they do. But basic GR has to be wrong because it's not a quantum theory. So black holes unquestionably exist. Whether there are singularities at the centers is a much more difficult question and has to be tackled by saying what you think quantum gravity might be like. And ditto for the early universe. I mean, if you just take the expansion naively, you're going to get a singularity 14 billion years ago. But to do a calculation, again, you need quantum gravity. We might make this the last one, do you think?
Okay.
Well, it's up to you. But anyway, go ahead.
Go ahead, Judy.
I'm impressed with the potency of looking back through all the discoveries and stacking them, seeing the saltations, and they kind of get more and more rapid. What's the next horizon? What's the next constant or the next eye-opener?
Well, I think the next step, obviously, in multiverses of some kind. Do I think we're going to have a quantum gravity theory next week? Well, probably not, but you know, there are an awful lot of people beavering away on these things with string theory and brain theory. B-R-A-N-E, not B-R-A-I-N. I think they have both, but there could be a breakthrough where we would have a serious theory of quantum gravity and could then tackle things like what happens inside a black hole, what was the very early universe like, and maybe are there wormholes, the physics of interstellar. Now, Kip Thorne and I wrote a paper, this is the guy who did Physics of Interstellar. Kip Thorne and I wrote a paper together 50 years ago, the only one we ever wrote together. We're going to do a 50th anniversary one this year. So you can see places where progress might be made. It's like ancient DNA from Neanderthals. How many of you really feel like you're 3% Neanderthal? I sure do. In fact, I think I might have a little higher percentage than most people.
All right, thank you very much, Virginia.